السلام عليكم ورحمة الله وبركاته، أسعد الله صباحكم جميعا. إن شاء الله اليوم مكملين معاكم بحل أسئلة sections 18.1 .2 .3 and .4 وهذا أول سؤال في هذول السكشنز. أوكي، فخلينا نبدأ بقراءة السؤال. So the system of three elements shown. So عندنا هنا element 1, element 2. So this is 1. Here we have 2. And here we have element 3. Okay, consists of 6 kilogram block B. So here is block B, element 1 or block B. So هذا block B, its weight is 6 kilogram. So B equal 6 kilogram, or it's written here. Okay, and 10 kilogram disc D. So this is the weight of MD. And 12 kilogram of cylinder C. Okay. If no slipping occurs, determine the total kinetic energy of the system at the instant shown. So we need to find T total kinetic energy. Total. Okay. So this is unknown. And here is the final answer. Okay. So let me move to the solving board. Okay, so and let me try to draw the three elements. So here we have the cylinder, okay, 12 kilogram, and here we have cord. This cord wrapped around the disc D. So this is cylinder C. Let me name it as C. And this one disc D, and it's hinged like this. So, and here we have cord. This is block B. Okay. Now we need to find T total. T total for this system, total kinetic energy, equal to the kinetic energy from block B plus kinetic energy from disc D and kinetic energy from cylinder C. Okay, so we'll go to them one by one and find its kinetic energy. So let's start with block B. Okay. So here is the whole system, and this one is hinged like this. Okay. So block B, it's written on the diagram or in the figure that velocity B equal to 0.8 meter per second. Okay, and its mass B equal to 6 kilogram. So T kinetic energy for block B, if I want first of all to write the general equation, which was half m Vg squared plus half Ig, okay, omega squared. Okay, so this is the general equation. Now this body, you can tell easily that this block is doing only translation. Okay, so if I go back to the PowerPoint, you can tell easily that block B is just translate. As this disc rolls, this cylinder rolls, okay, what will happen to this one? It will only translate. So the type of motion of this block is translation. So if I go back to the solving board, here you can come and say that the total kinetic energy for this block is due to translation only. There is no rotation. So this term will go to 0. So we end up with half mass of a block B, which is 0.46 kilogram, multiplied by velocity, which is 0.8 squared. Okay. So this is equal to, let me use my calculator. So 3 multiplied by 0.8 squared, which is 1.92 joule. Okay, so this is kinetic energy 1.92 for block B. Okay. Now let's move to the, so let me name this one as 2 and the first equation, this one as 1. So this is equation 1. Okay. Let's now move to disk D. Okay. Disk D, what do we have? Here is disk D. And here we have chord from this side, and here we have another chord from this side. Now, we can tell easily that this point, okay, this point on this disk, let me change the color, this point, has a velocity same as tangential, because the direction of this velocity is tangential, or sorry, it will be in the reverse direction, because rotation is like this. Okay, so this velocity has, or this point has a velocity same as block B. So if I name this point as, let me name it M, for example, this point. So velocity M must equal velocity of block B, and this is equal to 0.8 meter per second. Meter per second. Okay. Now, if I know this, I can proceed and say this velocity, which is equal to 0.8, must equal to omega multiplied by radius. Okay. Or I can say that W, or omega for the disk D, omega D, equal to 0.8 multiplied or divided by the radius, and radius from the drawing equal to 0.1 meter. Okay, so this is divided by 0.1, and from here I can say, let us go to the new page and use my calculator. Omega D equal to 8 rad per second. Okay. Okay. So here is the disk again, and here is hinged at the center. So what is the type of motion of this rigid body or this element? Rotation about fixed point. Fixed point. Second type of motion. Okay. So if I want to calculate kinetic energy, this is disk D, for the element, this is equal, the general, I will write the general equation first, half m vg squared, okay, plus half omega squared ig. Okay. Okay. But if we want to apply for this disk, what you can tell? You can tell easily that this term go to 0. Why? Because the centroid G, it is the centroid, is fixed. It's not rotate. So this term goes to 0. Let me go to the PowerPoint and show it to you. So this section was 18.1. Okay, so remember when we talk about the three type of motion, this is translation, and here is the equation. This is the general equation, by the way. If we have a translation, then this term, as we mentioned, equal to 0. If we have rotation about fixed point, see here the derivation of the equation was for our rigid body, which is fixed about point, which is non-decentroid. Okay, it is not centroid, it is O. So if I take the kinetic about G, this is the equation will look like this. This term will not vanish. Okay, this term will not vanish. Why? Because centroid has velocity. Okay, but if I want to write the kinetic energy of rotation about fixed point about O, then this term is vanished. Okay, so here, for example, if point G is fixed instead of O, then the equation of this type of motion is half mass moment of inertia multiplied by omega. Okay, so be careful for this. Okay, let me go back to the question. So here is the solving board. So continue here. So kinetic energy of the disk equal half the mass moment of inertia for disk. From where we can get it? We can get it from the 3D shape. So let me go back to the PowerPoint, and here is the mass moment of inertia for uniform shapes. So here, what do we have? We need we'll benefit from this shape, thin circular disk. Okay, and the axis that we have passes through the centroid, this axis. So I will take this equation. Okay, because we have similar condition. The rotational axis passes through the centroid, which is half mr squared. So let me go back to the solving board and write half multiplied by half mr squared multiplied by omega squared. And this is equal 1 over 4 mass for the disk equal to 10 multiplied by radius of the disk, which is 0.1, multiplied by omega, and we could find it earlier. Okay, this is why we find omega, which was 8. So I'll substitute 8, and please do not forget the square. Okay, this is equal to, now let me use my calculator. So 8 squared multiplied by 0.1 squared multiplied by 10 divided by 4. This is equal 1.6 joule. So this is the kinetic energy for the disk. I will name this equation as 3. Now let us proceed to the third element. The third element that we have is a cylinder that's rolling without slipping. All of them actually without slipping, but I will concentrate mainly on this one. So here is the centroid. Okay, here we have point that has a connection with the cord. Okay, and remember that those elements rotate or translate without slipping. That means this point has a velocity similar to the velocity of the translating block. Okay, so if this is done without slipping, if this is 0.8, that means this point is 0.8 again, this point here, and this point here is again 0.8. So if I want to name this point E, so VE equal to 0.8. Okay. Now let me erase this drawing. This information, the information given in the statement of this problem, rotate without slipping, uh, means that we have here instantaneous center of zero velocity, correct? So if this is the point of zero velocity, and before continue with this strategy, let me show you why I need to do or to benefit from IC point. So I need first of all to calculate the kinetic energy of this cylinder, and we name this cylinder as C. So this is C cylinder. So kinetic energy of cylinder C equal the general equation M half M Vg squared plus half Ig omega squared. Okay. So now in this equation there is two unknown, or there are two unknown. We have omega unknown, okay, and we have the centroid velocity unknown again. Okay. Okay. So we need to find them first. How to find them? Let me erase this equation. So we get to know that the tangential velocity VA is known, which is 0.8 meter per second. Okay. Now from this information, and if we know that this cylinder rotate without slipping, okay, if it is rotate without slipping, then VE using this relative equation equal VIC. Do you remember this equation? Plus VE with respect to IC, and this equal to 0 because this is zero velocity, instantaneous zero velocity, and the relative velocity VE with respect to IC equal what? Equal omega for the disk, omega C, multiplied by the relative position vector, which is RE with respect to IC. Okay, and here is V. So from this equation, we can find out omega C, which is VE 0.8, and this dimension equal to the diameter of the cylinder. The radius given 0.1, so the diameter is 0.2, and this is equal to 4 rad per second. Okay, so we could find the first unknown. Now the second unknown is Vg. Before going to the second page, so we need to find Vg. How to find it? Again, we'll find it based on the instantaneous center of zero velocity. Okay, so let me go to a new page and write down that Vg equal to omega of disk C multiplied by Rg with respect to IC. So omega G equal omega of the disk C equal to 4 multiplied by the distance, which is the radius 0.1, and the centroid velocity equal to 0.4 meter per second. Now we could find the kinetic energy of this cylinder C. Half the mass of this cylinder is 12, and the velocity of the centroid is 0.4 squared plus half. Now the mass moment of inertia again for the disk and for this cylinder, which is very thin cylinder, is same as the disk, which is half mr squared. Mass is 12, and the radius square is 0.1. Okay, 0.1 squared. Okay, multiplied by omega, which is 4 squared. So this is equal. Let me use my calculator. 0.4 squared, or do you know what? I'll calculate first the other part. So 12 multiplied by 0.1 square multiplied by 4 square plus 0.5 multiplied by 0.4 square multiplied by 12. This is equal 1.44 joule. And I will name this equation as 4. Now the final solution is to add, now substitute equations 2 and 3 and 4 in equation 1. You will find that T total equal T for the block plus T for the disk plus T for the cylinder, and this is equal to 1.92 plus 1.6 plus 1.44. If I add them together, I'll find that the total kinetic energy T total equal to 4.96 joule. Okay, I go back and check with the PowerPoint. Yes, this is 4.69.96. Okay, let's continue. So here another problem. So problem 18.3.2. So here in this problem, the bar shown below. So here we have a bar, as you can see, and this bar hinged from point O. Okay, so this point is fixed. It has no velocity. Okay, but it can rotate. Yeah, the bar can rotate about it. Okay, so the bar shown has a mass of 10 kilogram and is subjected to a couple moment of 50 Newton meter and force P equal to 80 Newton. Okay, so here we have a moment 50 Newton meter, and here we have external force which is 80 Newton, which is always applied perpendicular to the end of the bar. So هذه الفورس دائما perpendicular بغض النظر ثيتا هذه كم قيمتها. يعني لو كانت هذه ثيتا 0 completely horizontal bar، هذه الفورس بتكون ايش؟ perpendicular. لو كانت هذه ثيتا 90 كان البار بالتالي vertical completely. هذه الفورس دائما بتضلها ايش؟ perpendicular مع البار. Okay. Okay. So this is the meaning of this sentence, which is always applied perpendicular to the end of the bar. Also, the spring has an unstretched length of 0.5 meter. So this spring originally its length is 0.5. So this is, I can name it as LO or L original. Okay, 0.5 meter, and remains in vertical position due to roller guide at P. So هذا السبرينج بغض النظر وين كان موقع البار، لو كان horizontal ولا كان vertical ولا كان عند أي زاوية زي هذه الوضعية، دائما بيضل بالvertical position. يعني ما يعني إذا كان هو في البداية هون، okay، وأنا بديت أحرك في البار أعرض عليه قوة، هذا السبرينج مش راح يحصل له inclination ويضل بنفس المكان. في عندي هنا رولر وإلها مجرى، إلها مسار، هذه الرولر بتتحرك، وبالتالي هذا بتحافظ على حركة على البوزيشن للسبرينج in vertical position. Okay. So this roller slides inside this channel. Okay, slides in this channel. بالتالي, as a result, the spring remain in vertical position whenever the bar, uh, whenever the location of the bar. Okay. طيب. So this is the meaning of remains in vertical position due to the roller guide at B. Determine the total work done by all the forces acting on the bar when it has rotated between theta 1 equal to 0 up to theta 2 equal to 90. We mentioned earlier that work happens between two states, so it depends on the band. So it starts from theta equal to 0, completely horizontal, and ends up when it's completely vertical. Okay, لما تكون الزاوية 90. So هذه state 1. Okay, وهذه state 2. Okay, so ايش المطلوب؟ Determine the total work. So total work total شو تساوي؟ done by all forces. راح نشوف كمان شوي نرسم free body diagram ونشوف كل الفورسز والمومنتس اللي بتأدي لحدوث work. حكينا بالسابق في المحاضرة الماضية إنه في عنا works certain forces بتعمل شغل، بتعمل work، وفي عنا forces ما بتعمل. Okay. So كيف نعرف من الفري body diagram. So let's move to solving board. خليني أفتح a new page or a new document. Okay, and let me draw the free body diagram first. Okay, so here is the drawing. قبل لا نروح لستيت 1 وستيت 2 خليني في البداية أشوف إيش هما ال forces affecting on this rod. Okay, now we have force at the end of this bar, force B. Okay, we have spring force in this direction, F spring. Okay, we have weight exactly at the middle. Okay, I can name even this point as G. So here we have weight. Okay. By the way, if I go back to the, this is not W, sorry. We agreed last time that the work is U. Okay. So let me go back to this board. So yes, this is weight. Okay. What else? We have moment, M, and we have reaction forces. I will assume them in positive directions, and this is X direction. Okay, so I'll ask you the question now. Which of these forces will do work? Okay, between state 1 to state 2. Of course, the reaction force on a fixed point that will not do any displacement will equal to 0. Okay, there is no work due to reaction force. Now, the spring force, once it translate the bar translate between state 1 or location 1 to state 2, then the spring will, here is the spring, okay, and here is the new location of the spring. So we have certain displacement, okay, in the y-axis from this point to this point, okay. So we have certain elongation, sorry. So you can notice the difference in the length of the spring. So do we have displacement in the same sense or in the same direction of force, Fs? The answer is yes. So then we have work. Okay, now let's see. So yeah, we erase everything and write down that work 1 to 2, we have work due to spring plus. Do we have work due to external force B? Force B, this one. So you can notice easily that force B remain vertical and move with the bar. So the bar moves like this. So the force each time it is it translate with the with this track. This is the track. Okay. So there is displacement and there is load, and we can this force can produce work. Okay. So yes, we have work due to load. Okay, because we have displacement. Okay. How about weights? Weights the same. Okay. Here is the weight. Okay. Where is the weight? Here is the weight at the beginning. And at the final stage, here is the weight. And there is certain displacement in y-axis. Okay, between the first and the final state, which is y. And this displacement in the same direction of w, then we have work due to weight. Okay, how about moment? Moment the same, because we have theta equal to 0 and then we have theta equal to 90, then yes, we have moment. So at the end, we can conclude that this is actually, you can do it before start solving. Okay, so at the end, we can tell that there is no work due to reaction, there is work due to moment, there is work due to spring force, there is work due to weight, and there is work due to load. Okay, let us start solve them one by one. Okay, and let me erase this one first, and then we'll move to the first lot. Okay, so here is the bar. I'll start first with the moment. Okay, I'll start with the moment. So work due to moment, we learned before that it's equal to moment, which is constant in this scenario. Otherwise, I'll take the integration. Theta 2 minus theta 1. Okay, which is the easiest one. So the moment that we have is equal to 50 Newton meter multiplied by, now theta 1 equal to 0. Let me use another color. So here is state 1 and here is state 2. Theta 1 is state 1 equal to 0. And in state 2, theta 2 equal to 90 degree. And we should convert this value into rad. So we multiply it by pi and divide by 180. So here is 2. So pi over 2 rad. Okay. So I'll substitute here pi over 2 rad. So the answer now is, so 50, what is it? 50 multiplied by pi divided by 2. And the answer is 78.5 joule. Okay, so this is work due to moment, and I will name this equation as 1. Okay, let's now move to the other force. Okay, so here is the state 1, and here is the state 2. State 1 and state 2. And let me look now to the weight. Weight exactly on the centroid, and this is equal W, and here is the new location of the centroid. So this is G, and here is the new location. Now there is vertical distance equal to if the total length. Where is the total length? Let me go back to the slide. So here is the slide. So the total length is a 3. So the middle distance is 3 over 2, which is 1.5. So here is the distance, 1.5 meter. And if I want to go to the equation, so work due to weight equal to plus or negative. Let me write first W multiplied by delta Y, the equation of this force. But is it minus or positive? It is positive. Why it is positive? Because W, okay, directed downward, and the displacement that happens between state 1 and state 2 directed to the negative y direction. Okay, so here is the direction of this displacement. So both of them in same direction. So I'll substitute it as positive. Okay, so let me calculate the weight, which is equal to mass of this bar, which is 10 kilogram, multiplied by 9.81, multiplied by the distance, which is 1.5. Using calculator, this is 98.1 multiplied by 1.5 equal to 147. Okay, 147.15 joule. And I will name this result as 2. Okay, now let's move to another state or to another force. So we end up with the spring and with the external load. I'll start with the external load. So here is the external load B. The point that this work affected on is the edge of this bar, and here is the load on state 2. So here is state 1, and here we have state 2. Okay. So the work due to load, I write it like this, equal to the force that we have multiplied by the distance or the displacement. Okay, the displacement here one can easily tell once this force is perpendicular, then it remains perpendicular at any instance along this arc. Okay, once it is parallel to this arc, okay, because at any instance, for example this instance, okay, the force is perpendicular, so the force remain walk or directed with the same direction of this path, okay, until it reach the final state. So we need to calculate the length of this arc. How to calculate this length? S equal to R multiplied by theta, isn't it? So R here equal to the length of this rod, which is 3 meter, multiplied by pi over 2. And if I use my calculator, so 3 multiplied by pi over 2, okay, which is 4.72. So work due to load equal to the external load is 80 Newton multiplied by S, which is R multiplied by theta, and this is equal 4.712. And this is equal to multiplied by eta, or 80, sorry. This is 300, almost 77 joule. Okay, this is work due to external load. I'll name this one as 3. Okay, now we'll end up with the work due to spring. Work due to spring force. So here is this channel that the roller is slide inside. Okay, and here is the rod. I'll draw it in another color. So here is the rod in state 1. Okay, and here is the rod in state 2. So this is 1, and here is state 2. So the rod in state 1, if I go back to the slide, here's the slide, I'll notice that this is the distance between the channel, this channel, okay, where the roller is sliding, and the point A, the fixed point, 0.75. And it's mentioned in the statement of the problem that the original length of this spring is 0.5. How we can benefit from these two information? So this distance is 0.75. Okay, and L original, let me erase this one for the time being. And L original is 0.5 meter. So what do you think? Is it in state 1? Because you know that the work due to force, spring force, is always minus half, okay, S2 squared minus S1 squared. Stretching, this is stretching in state 1, and this is stretching in state 2. And this is the stiffness. Okay, remember this equation from the slide. So do we have stretching in state 1? If the original length is 0.5 and this distance is 0.75, so do we have S1? The answer is yes. So if this rod is completely horizontal and this distance is 0.75 and the original length is 0.5, then we have S1 equal to 0.75 minus 0.5. And S1 is equal, as a result, to 0.15 meter. Okay, so this is the stretching for the first scenario. Okay, or sorry, this is 0.25. 0.75 minus 0.5 is 0.25. So now, how about state 2? State 2. Do we have stretching? Of course, yes. Okay, let me use another color. Here is another color. Now in state 2, here is the ruler, and this spring remain vertical, and it is connected into this point. If I go back to the slide, this point is located at 2 meter, okay, from point A. So this distance is 2 meter, okay, and this distance is 0.75. Do we have stretching? Yes. So S2 equal to final length, which is 2.75, the total length. This one, oops, this one plus this one, okay, minus the original length, which is 0.5. Okay, so stretching in state 2 is equal to 2.25 meter. Okay. Now, the work happens due to spring force equal to minus, because always in the other direction of the displacement, minus k s2 squared minus s1 squared. So the stiffness in the statement of the problem was mentioned that, first of all, let me write minus half. K is given in the statement of the problem, which is 30 Newton meter. Okay, it's written on the figure of this problem. Multiplied by stretching 2.25 squared minus 0.25 squared. Okay, and the answer, let me use my calculator. So minus 0.25 squared multiplied by 15, this is equal minus 75 joule. This is from spring. And I will name this one as 4. So the total work happens due to all of these forces. U total equal to U due to moment plus work due to weight plus work due to external force plus work due to spring force. So work due to moment equal to 78.5 plus, and here you can write substitute equation 1, 2, 3, and 4 and the following equation. Okay, so 78.5 plus 147.2 plus work due to load equal 377 plus work due to spring, which is minus 75.0. Okay, there's no point. So this is 377 plus 147.2 plus 78.5. So the total work is equal to 527.7 joule. Okay, so this is the total work. Let me check with the slides. Yes, almost equal to 528 joule as a total work. Now in the previous example, we saw together how to find total kinetic energy. Okay. Now in this example, we could see how to find out work due to different source. Okay. Now let's see a problem that is combine kinetic energy and work together. And I think you remember what we call this combination. Do you remember what we call this combination? If we combine kinetic energy and work together, we call it principle of work and energy will benefit from this equation. So first of all, you need to calculate each one alone and then combine them together in this equation. We'll apply this equation in this problem 18.4, but I'll not do it today. I'll do it next lecture. So next lecture I will solve this problem and then I will move on to a new section and the last section of this chapter, section 18.5. Okay, until then, stay safe and see you soon.